Hi everyone, welcome to part 2 of the series on differential calculus in Python. Today I would like to make it more practical, so I plan to edit and run a Jupyter notebook as we go. One of today's main topic is how to write a custom autograd function in PyTorch. Okay, so first we import torch, of course. And then if we know nothing about how to write such a function, the first thing we'll do is maybe to Google. And I have already chosen this one that we will follow along. This is a notebook on the internet, and by the look of it, we can guess it might be some kind of an IBM course. A course note or exercise from the IBM. Yeah. And if we go to the end of the notebook, we'll see some advertisements of IBM, and here is the author of the notebook, and it says that the author is someone who's working for IBM and also has a PhD in electrical engineering. Yeah. So it seems to be a pretty reliable resource. So let's see what we can learn from it. In the beginning, it just introduces the basic concepts of PyTorch autograd, how to do differentiation. Yeah. We already introduced them in part 1, so we skip it, and here is the template I want. Yeah, so I'll simply copy it and paste it to my notebook, and I'll explain. Okay, so to define or to write a custom autograd function in PyTorch, the most straightforward and the easiest way is to do it in Python, and to inherit the class of torch autograd function here, like this. You define a new class, and you inherit from this function class, and you should define two methods. Named forward and backward, and by the name of it, we can easily guess what each one of them should do. Forward is just you return the function, how the function maps its input, and backward you define in the backward method you define the differentiation. That is, you return the derivative, yeah, or the gradient. So this SQ class from the author is simply an toy example. It tries to redefine the square function, though in PyTorch people already defined torch.square. We can use this toy example to test our understanding. Yeah. So the input argument of the forward method, there are two. One is context, the other is I, which stands for input. That is like x with respect to f of x. Yeah. So So apparently here we should return I squared. So what it does is it saves I squared into result and it returns results. And in another line it saves I into the context for later usage in the backward method. And in the backward method, there are two input arguments, context and grad underscore output. And what the author does is it pops out the I, and then it returns 2I. From calculus, we know that the derivative of I squared is 2I, so this seems to be no problem. Yeah. But there's one thing I'd like to modify, which is the variable here, because it saves 2I into grad output, which overrides an already existing variable here. So I don't like it. Maybe I'll make it grad. Okay. Next, I'd like to write an easy test for this function or this class, and to test if it gives the correct gradient. By correct, I mean I'll compare with PyTorch answer, since PyTorch is a well-known and well-established library, so we can kind of trust its result being correct. So I'll call my test test cube first, and its input argument will be a function f, and at which point we should do the derivative. Yeah. And by the way, actually for better generality, we should consider this I as an array and not as a single number. They'll be more general, but for today's tutorial, it's fine if we take it as a single number. That is, we were just doing like one-dimensional calculus. Yeah. So what do? We do like x equals first tensor at required grad equals true. We initiate the variable in PyTorch, and then we define the mapping. Yeah, we do cube first, so cube, and then we put it into f. Cube first means cube first, f later. Then we do differentiation in PyTorch, and then we extract the implemented variable stands for derivative or gradient, or implemented gradient. This should be equal to, I think, like this. Yeah. Let me edit somewhere else, maybe. I use another editor here because I'm more familiar with it. So once we have the implemented derivative, I like to also have the expected derivative. That is the answer from PyTorch. So we do the same. We initiate a variable, and then Yeah, okay. We do this, and then it's pretty much the same. Okay, and at the end we simply print the result with another function which we define here. If they're equal, then we print that the test is passed. We also print their common value. There you go, equal to the second decimal point. Otherwise, we print failed, and we print their respective value. Okay, and actually here I forgot something. Oh, well, I do this because I like to be able to put into this F the class we just defined, the SQ class, or a simple PyTorch function. So this condition is just to convert the class into a function whenever I put in into this argument a class subclass of torch autograd function. Yeah. Let's copy from our editor and paste it here, and we'll try our first test on the SQ class. Oh, yeah, it says inspect is not defined, so that's because I forgot to import. Yeah, so let's run it again. So it says passed. They both equal to 192. Okay. So actually, it's we can also manually check the answer, because this is just how to say, x maps to what, x q first and then square. So the derivative should be what? Should be by chain rule we have 2 times x to the 3 and 3 x cubed. It's like this. So 2 times 2 to the 3 times third times 3 times 2 square equals 192. Yeah. And we can also, as we said, we can put in other PyTorch defined functions. So yeah, we should pass the test. and also we can also pass a lambda function like this, and we should pass the test as well. Yeah. Okay. So seemingly everything is fine. We passed the test, and implementation of the SQ class seems to be perfect. But if you are careful, you might notice that in the backward method there is an input argument called grad underscore output, but we've never used it. And actually, grad output is like in the chain rule. You differentiate the composite function G circle f. You have G prime and multiply by another f prime. So the grad output here is like the G prime, and we discarded it in this method. Well, actually we should keep it. Combine the grad output with the current gradient of our SQ function. So let's look at an example that might example or a test that might break this. So okay. So we'll look at a similar test which maps x to the x squared, and then we take the cube. Yeah. So I'll call the test or what? I'll call it test cube later, and it will be a similar function. I just take the square first, and then the overall result I'll take a cube. So here is the same, and we compare it to, yeah. Okay, right. And let's test this against SQ. So it says that SQ failed in the test. The implemented derivative is 4, while the expected derivative is 192. Yeah, and indeed, if we write this more correctly, it's like this. Square times 2x. The derivative should be equal to this thing. Yeah, so we should expect that it should, the correct answer should be x squared times 2 times x. Oh, right. This, yeah. Okay, so it's still 192. But SQ failed the second test. We can see that whether PyTorch definition will pass the test. Yeah. So it passed the test, and also the lambda function also passed the test. So our definition of the square function is probably wrong. Yeah, and the reason is that as we just mentioned, we simply discard the grad underscore output, which is here is this part 3 parentheses x squared raised to the second power, we just discard this part. So that's why we have the answer 4, because we only return 2 times x. So so we know it's incorrect, and we also know how to make it, how to modify it. So let's do define a new class called more correct sq. We only have to change the backward method into grad equals grad output times 2i. Yeah. So we have to define its forward method, and since we do not make any change, we can do it like this. Yeah. Okay. So okay, once we define this, we can run the 2 tests we just defined and see if the new class passed both of them. Later. Yeah, great. It passed both of them. So far this is a better implementation. But is it already a correct implementation? I mean, does there exist any other test that it does not pass? Oh well. If we still remember, we have talked about how to say GitHub PyTorch. In part 1, we have looked at this file, tools autograd derivatives. So let's see, tools, this is the PyTorch source code, tools, autograd derivatives. So remember that in the past we look at in part 1 we look at this file, which defines the derivatives, lots of different derivatives of lots of functions, like absolute value function, arc, cosine, etc. And we see often this conj thing, and we mentioned that this is a complex derivative. Yeah. So here apparently we only consider in the implementation of these 2 classes of square functions, we do not take into consideration of complex numbers. Yeah. So since we did not consider a complex case, it might fail a test which involved a complex number. So let's try to define such a test. Yeah, so I'll copy the tests and complex input. So let's change the add point to be a complex number in Python. And also I kind of need another function which guarantees that the overall loss function or the overall composite function will return a real value. So I'll do it like this. and then here will be like this. Torch square x, and we compare them. Yeah, and the reason why we must wrap the result of f of x into another g is because PyTorch has not yet allowed differentiation of a complex value function. So we have to make sure that the final output is a real number. So here we use the torch absolute value to ensure that the result is the absolute value of a complex number, which is guaranteed to be real. Yeah. So here is the test, and let's see if let's see if more correct pass the test. So you see the result, it failed the test. Yeah. On the other hand, you can test if lambda pass the test, and indeed it's passed the test. So we can still improve the class. Yeah, but how? Well, actually, like this. Should work. It should work if we do it like this. We simply add this conj. Yeah, it should work like this. Yeah. Let's see if this really works. Yeah. Even more correct. Yeah, it passed. And I'll explain later why we should add this. But for the moment, let's test the other two tests to see if this even more correct SQ is indeed passed the first two tests. Okay. So the last class, the newest class we just defined here, passed all three tests so far. Yeah, so similarly it is the most correct until now. And now I'd like to discuss why we should add this thing. Yeah, here. And allow me to find a web page, the famous autograd tutorial. So, in order to understand why do I know we should add this, there is a section in this famous autograd mechanics article that we also mentioned in part 1. This section is named autograd for complex numbers, and it's actually quite lengthy, so we wouldn't have time to go through all of it. Yeah, but the important thing is this Wirtinger Calculus. Yeah, It's called Wirtinger Calculus. Apparently because it's not the calculus that we are used to. Yeah. And I also won't spend much time on what Wirtinger Calculus is, partly because maybe people watching this video doesn't care about it because they might be more engineer minded. They don't really care about proving the theoretical things themselves. They rely on the works of theorists. So in this case, there is only one thing that is important. That is in calculating the gradient of loss function in PyTorch. Here, the function L. What we do is that we regard if in L there in some steps, in some intermediate steps, there is complex numbers involved. Or here is in the shallowest layer there is complex number involved. When you want to do the gradient, you want to calculate gradient, you treat z and z star as independent, as if they were independent variables, and you calculate partial L, partial z star to obtain the gradient. That is, the gradient in PyTorch is calculated this way, and equation 4 is the only important thing for people who are more engineer minded. It says that it equals grad output star times partial s partial z star plus this. It's kind of like a product rule. Yeah. So only this matters. So if we were engineer and if we temporarily believe this formula, let's see what we will obtain. I think we will obtain exactly this. Yeah. Allow me to copy some existing text thing. Yeah. Okay. So in our case, we have in the test of test complex input, we have a G, which is torch absolute value, and F. So we are our loss function is G circle F. G circle F, and F is the square function. G is the absolute value function, and equation 4 can be written as this. Yeah, and here the intermediate S is simply F. So we see that if we treat z star and z as independent variables, then this f function has no z star. So differentiating it with respect to z star gives 0. So the left term 0 out, and the right term we can calculate it as a grad output times 2z star. Yeah, and this is exactly why we write 2i.conj. Yeah. Okay. Oh, by the way, I forgot to mention one thing here in my repo. notebooks parts. We're in part 2. So I have backup the Jupyter notebook from IBM here, because maybe someday their links will be will disappear. So I back it up here. It is the original notebook, and what I just wrote in this untitled 2 .ipynb is here, so you can check it out after the video. Yeah. Okay, this is what I'm going to mention, and also in here it is better, like more precise. Yeah, better written, because I spend more time editing it than I do it here. Edit and execute them on the go, and so there will it will contain more things in case someone is interested. Yeah. So yeah, let's go back to Wirtinger Calculus. That's the last thing I'd like to talk about a little about. If the reader is interested in Wirtinger Calculus, he or she could read this article, this section in the article. But to be honest, if you during your first lectures of this article, if you find it difficult to accept, please be assured you're not the only one. Me too. During the first few lectures, I find it kind of difficult to accept, or I'm not convinced by the derivations in this article. Not because it's wrong, but because I have some doubts. And the biggest doubt is that why we can, in Wirtinger Calculus, we can do things like partial z, partial z star, as if z and z star are independent variables, just like we do in 2-dimensional differential calculus. We can do partial x, partial y, like they are independent. Yeah, and for this, I also edited a notebook, Jupyter notebook, with only LaTeX content, which tries to convince myself. It's like a note for myself. Try to persuade myself that actually it is valid to do partial z star. Yeah, and if the audience of this video is interested in this part, and if they seem not to be able to find some other resources talking about this, maybe they can refer to this notebook. I have spent quite some time editing it, so I hope this can help them. The most important concept from this notebook is that in Wirtinger Calculus we're not doing exactly complex analysis or complex function theory. What we do in Wirtinger Calculus is that we want to regard a function f of z, which sends a complex number to to the real number field. And in this case, we can regard it as we can regard f as from R2 to R, and we can use if f is real differentiable, then we can still compute the gradient regardless that f is from C to R. Yeah, but sometimes, for example, if the function f equals the absolute value of z bar, then or some other complicated expression, then it is quite tedious to express as z in terms of x and y, and then do the computation of a derivative. So Wirtinger looks for a way to do the gradient in terms of z and z bar, and it just so happened that in the derivation we can treat z and z bar as independent. Not that they are really independent, but like by luck, we can treat them like this, and the derivation just goes well. So so it's like this. Yeah, I hope I try to illustrate the important point, and if it's not, just never mind. Yeah. Okay, and one last thing maybe I could mention is that, as I just said, for the gradients in PyTorch, it calculates this partial L partial Z star, and it mentions in this article that Jax does it differently. Yeah, so let's look at Jax a little bit. So we still have, for example, let's still do the absolute value function. We try to calculate the gradient of the absolute value function at 3 plus 4j, and let's see what's its value, and we also do the same in PyTorch. Yeah, and see its value. So we see that they give different results. In Jax it's 0.6 minus 0.8j. In PyTorch it's plus 8j, 0.8j. Yeah. Another example could be the imaginary part function. So if we run it, it's still different. Yeah. So as the last thing in this video, I just want to mention this, and this is the end of part 2. Hope to see you very soon in part 3. Bye bye.